Today, we are exploring one of the most essential skills in AP statistics. Topic 4.5. Carrying out a test for a population mean or population mean difference. By the end of this lesson, you will be able to calculate a test statistic and p-value for a population mean. You will also learn how to interpret that p-value in context and justify a statistical claim by comparing it to a significance level. When we don't know the population standard deviation, which is almost always the case in the real world, we use the t-distribution. This is what we call a one-sample t-test. Whether we are looking at a single set of data or the differences in a paired dataset, the logic remains the same. We are testing a claim about a mean value. To perform a hypothesis test, we need a way to measure how far our observed sample mean is from the hypothesized population mean. The tool we use is the t-statistic. The formula for the test statistic, t, is t equals x bar, which is our sample mean, minus mu0, the value from our null hypothesis. We divide that difference by the standard error, which is the sample standard deviation, s, divided by the square root of the sample size n. An important detail when using the t-distribution is the degrees of freedom. For a one-sample test, the degrees of freedom is simply n-1. Think of the t-distribution as a cousin to the normal distribution. It's symmetric and bell-shaped, but it has heavier tails to account for the extra uncertainty that comes from using the sample standard deviation instead of the populations. As your sample size n gets larger, the t-distribution looks more and more like the standard normal distribution. But for smaller samples, those degrees of freedom are crucial for accuracy. Once we have our t-statistic, we need to calculate the p-value. The p-value is a probability. Specifically, it is the probability of obtaining a test statistic as extreme or more extreme than the one we observed, specifically in the direction of our alternative hypothesis. Given that the null hypothesis is actually true, imagine the null hypothesis is the truth. The p-value tells us how surprising our sample data is under that truth. If the p-value is very small, it means our observed data would be very unlikely to happen by pure chance if the null hypothesis were true. To find this area, we can use a t-distribution table, but in most modern contexts and on the AP exam, you will likely use technology, such as the t-test function on your graphing calculator. The direction depends on your alternative hypothesis. If you are testing if the mean is greater than a value, you look at the right tail. If you are testing if it is less, you look at the left tail. And if you are testing if the mean is simply different, you look at both tails and double the area. Now that we have our p-value, we have to make a decision. This is where we justify a claim about the population. We compare our p-value to a predetermined significance level called alpha. Usually, alpha is set at 0.05, but it can vary. If the p-value is less than or equal to alpha, the result is statistically significant. We reject the null hypothesis. This means we have found convincing evidence for the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. Notice we don't say we accept the null. We simply haven't found enough evidence to throw it out. When you write your conclusion, you must always include these 4 parts. Use non-definitive language like, we have convincing evidence, or we do not have convincing evidence. Never say we have proven anything. Since the p-value of 0.03 is less than alpha of 0.05, we reject the null hypothesis. There is convincing evidence that the mean height of all plants in this greenhouse is greater than 20 centimeters. Notice how this conclusion refers back to the specific population and the specific parameter we were testing. Let's put this into practice with a detailed example involving a single population mean. In this scenario, a light bulb manufacturer claims their new bulbs last 1,200 hours. A consumer group suspects the bulbs last less than 1,200 hours. They test a random sample of 25 bulbs. In this scenario, the consumer group wants to see if there is evidence that the mean lifespan is lower than claimed. From the sample of 25 bulbs, they found a mean of 1180 hours with a standard deviation of 60 hours. We will use a significance level, alpha, of 0.05. First, we define our hypotheses. The null hypothesis is the manufacturer's claim that the mean is 1,200. The alternative hypothesis reflects the suspicion that the mean is actually less than 1,200. Before calculating, we ensure our conditions are met. Since we have a random sample and a small sample size from a large population, we proceed with the t-test assuming the population distribution of bulb lives is roughly normal. Now, let's calculate the t-statistic. Our formula for the test statistic is x bar minus mu sub 0 divided by the standard error. Plugging in our values, we get 1180 minus 1200 over 60 divided by the square root of 25. This simplifies to negative 20 over 12. Our calculated t-score is negative 1.667. This tells us our sample mean is about 1.67 standard errors below the hypothesized mean. Using degrees of freedom of 24, we look for the area to the left of negative 1.667 on a t-distribution. Using technology, we find the p-value is approximately 0.0543. Since 0.0543 is greater than our alpha of 0.05, we fail to reject the null hypothesis. Even though 1180 is less than 1200, the difference wasn't large enough to rule out random chance at the 5% significance level. Now, let's look at a different type of problem: testing a population mean difference using paired data. This is common in before and after studies, or matched pairs designs. In this case, we don't have two independent groups. We have the same 10 students measured twice. We are interested in the mean of the differences. Here are the improvement scores for each student. A positive number means the score went up. From this data, the average improvement was 3.4 points, with a standard deviation of 2.63. Let's use alpha equals 0.05 to see if this improvement is statistically significant. The null hypothesis is that the course makes no difference, so the mean difference is 0. The alternative hypothesis is that the mean difference is greater than 0, meaning the course helps. Next, we calculate the t-statistic. Our t-statistic is 4.088. This is quite high. It means our sample mean difference is over 4 standard errors above 0. Using 9 degrees of freedom, we find the area to the right of 4.088. The p-value is approximately 0.0014. Because our p-value is much smaller than alpha, we reject the null hypothesis. The small p-value tells us that an average increase of 3.4 points would be very unlikely to happen by luck if the course actually did nothing. There is convincing evidence that the memory course improves test scores for the population of students. Let's take a deep dive into how to interpret a p-value correctly. This is one of the most frequently tested concepts on the AP exam. Remember the formal definition. The p-value is the probability of obtaining a test statistic as extreme or more extreme than the one observed, assuming the null hypothesis is true. Suppose we are testing if the mean weight of a bag of chips is 50 grams, and we get a p-value of 0.02. This interpretation must include 3 specific things. First, the context of the problem. Second, the explicit assumption that the null hypothesis is true. And third, the probability of the observed result or something more extreme occurring. A common mistake is thinking the p-value is the probability that the null hypothesis is true. That is incorrect. The p-value is a probability about the data, not about the hypothesis itself. Similarly, it is not the probability that the alternative hypothesis is true. Instead, think of it this way. If the p-value is very small, it means that what we observed is so unlikely to happen under the null hypothesis that we start to doubt the null hypothesis is true at all. That is why we reject it. Take a moment to think about this. If I told you a coin was fair, but I flipped it and got 10 heads in a row, the p-value for that result would be very small. You would likely reject my claim that the coin is fair because what you just saw is too rare to be a coincidence. To ensure you are fully prepared for the AP exam, let's work through a comprehensive example from start to finish. A nutritionist claims that the average sugar content in a certain brand of cereal is 12 grams per serving. A health advocate believes the average is actually higher. A random sample of 36 servings is tested, finding a mean of 13.1 grams and a standard deviation of 4.2 grams. First, we identify our parameter of interest. Here, mu represents the true mean sugar content per serving for all cereal of this brand. The null hypothesis is that the mean is 12 grams. The advocate suspects it is higher, so our alternative is that mu is greater than 12. Since our sample size is 36, which is at least 30, the central limit theorem tells us that the sampling distribution of the sample mean will be approximately normal regardless of the shape of the population. Now we calculate the test statistic. Our t-statistic is 1.571. This means our observed mean of 13.1 is 1.571 standard errors above the hypothesized mean of 12. With 35 degrees of freedom, we find the area to the right of 1.571. The p-value is approximately 0.0626. Because 0.0626 is greater than our significance level of 0.05, We fail to reject the null hypothesis. There is not convincing evidence that the true mean sugar content of this cereal is greater than 12 grams per serving. Even though 13.1 is higher than 12, this difference could reasonably be attributed to sampling variability. We don't have enough evidence to call the nutritionist a liar. Let's look at another important application, comparing two different conditions for the same group of individuals. This is called a matched pairs t-test, and it's a specific type of one-sample t-test performed on the differences. Does listening to music while studying affect test scores? 8 students take 2 similar tests, one while listening to music and one in silence. The order is randomized for each student. Here, we aren't comparing two separate groups of people. We are comparing the same student's performance under 2 different conditions. This helps control for individual differences in intelligence or test-taking ability. We calculate the difference for each student. If we subtract silence from music, a positive difference means they performed better with music. The mean difference in our sample is 2.375 points. Is this increase large enough to be statistically significant, or is it just random noise? In this case, let's test if there is any difference at all, which makes this a two-tailed test. The null is that the mean difference is 0, and the alternative is that the mean difference is not equal to 0. Our t-statistic is 2.259. Because our alternative hypothesis is not equal to, we must find the area in the tail and double it. Using technology, the p-value is approximately 0.058. Since 0.058 is slightly greater than our alpha of 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that there is a difference in mean test scores between listening to music and studying in silence. Note how close this was. If we had used a significance level of 10%, we would have rejected the null. This highlights why choosing your alpha before the experiment is so important for integrity. In statistical testing, the significance level, alpha, acts as our burden of proof. Let's look at how changing our requirements can change our conclusions. Imagine an inspector tests a water source. The legal limit is 15 parts per billion. The inspector suspects the lead level is higher. With a sample mean of 16.2 and a standard deviation of 3.8, we first calculate the t-statistic. Our t-statistic is approximately 2.0. Now we find the p-value with 39 degrees of freedom for a right-tailed test. The p-value is 0.0264. Now, let's see how different alpha levels lead to different actions. If we use the common 5% significance level, our p-value is smaller than alpha. We reject the null and conclude there is convincing evidence the water is unsafe. However, if the city requires a more stringent 1% significance level to avoid expensive shutdowns, we would fail to reject the null. We would say there is not enough evidence to prove the water is unsafe at the 1% level. Choosing alpha is a balance. In the water example, a higher alpha might be better because we want to be very sensitive to safety risks. In a court of law, we use a very low alpha because we only want to convict if the evidence is beyond a reasonable doubt. This prevents researchers from p-hacking or picking a significance level that happens to support the result they wanted to find. To wrap up, let's look at one final, comprehensive example that pulls everything together, including the interpretation of a p-value in a context where we fail to reject the null hypothesis. We are looking at new battery technology. The claim is that the average charging time is 30 minutes. We test a random sample of 15 batteries and find a sample mean of 31.5 minutes, with a standard deviation of 2.4 minutes. We will use an alpha level of 0.01. First, we define our parameter. Mu is the true mean charging time for all batteries of this new type. Step 1 is to state our hypotheses. The null hypothesis states the mean is 30 minutes. We are testing to see if the charging time is actually longer than claimed. Step 2 is to calculate the t-statistic. We plug in our values to the formula. Our test statistic is 2.421. Step 3 is to find the p-value. With 14 degrees of freedom, we find the p-value using technology. The p-value is 0.0148. Now, let's provide a formal interpretation of this value. Assuming the true mean charging time is 30 minutes, there is a 0.0148 probability of getting a sample mean of 31.5 minutes or higher simply due to random sampling variability. This interpretation acknowledges the null is true, uses the specific sample mean, and mentions the probability of that result or higher. Step 4 is the decision and justification. Since 0.0148 is greater than our chosen significance level of 1%, we fail to reject the null hypothesis. Finally, step 5 is the conclusion. There is not convincing evidence that the true mean charging time for these batteries is greater than 30 minutes. While the sample mean was 31.5, It was not significantly higher enough to rule out chance at the 1% level. Let's review the key takeaways. 1. Identify the parameter and hypotheses. 2. Check your conditions. 3. Calculate the t-statistic and p-value. 4. Compare the p-value to alpha. And 5. Conclude in context using non-definitive language. Following these steps every time will ensure success on your AP Statistics exam and a deep understanding of how statistical claims are justified. Good luck with your studies.